Ever drop a magnet through a copper pipe
Mhm.
and notice how it falls super slowly, almost like it's resisting like gravity or something?
Yeah.
That's electromagnetic induction. It's
Uh-huh.
the same principle that lets us generate electricity in power plants.
Crazy. Right.
Yeah. We're actually going to unpack how that works today.
Okay.
By focusing on a specific example, a long magnet falling through a ring,
Yeah.
we'll be using some really cool interactive simulations
Other simulations.
and teaching materials from open educational resources and open source physics at Singapore.
Oh, those are great.
Yeah.
It's a surprisingly simple setup,
Yeah.
but it illustrates some really fundamental principles of physics.
Okay, so let's picture this. A long magnet falling through a ring.
Okay.
Simple enough, right?
Yeah.
But here's where it gets interesting. Magnets, as we know, create an invisible magnetic field around them.
Right.
What's important here is that as the magnet moves through the ring, this magnetic field is constantly changing.
And that change is what kicks off the whole process of electromagnetic induction.
Okay.
It's like a chain reaction.
Oh, okay.
The moving magnet changes the magnetic field,
Uh-huh.
and that change creates an electric current in the ring.
Okay. That makes sense, but how much electricity are we talking about here?
Yeah, good question. That's where Faraday's law comes in.
Okay.
Basically, it tells us how much voltage, think of it as the push behind the electric current,
Right.
gets created based on how quickly the magnetic field changes.
Okay.
The faster it changes, the stronger the voltage.
So if I were to, like, say, drop the magnet from higher up, making it fall faster,
Yep,
would that create a stronger voltage in the ring?
exactly. You're getting it.
Yeah.
Now, there's another piece to this puzzle, Lenz's law.
Oh, okay.
It tells us the direction of that induced current.
All right.
And get this, it always opposes the change in the magnetic field.
Oh, really?
Yeah, it's like the ring is trying to fight back against the falling magnet.
Hold on. So the current in the ring is actually creating its own magnetic field to, like, push back against the magnet.
Precisely.
That's why it falls so slowly.
It's like an invisible braking system.
Wow.
This is a really important concept because this principle of opposing forces is used in so many technologies.
Yeah.
From like wireless phone chargers
Uh-huh.
to those giant generators in power plants.
Wow. Okay, my mind is already a little blown. Now, the simulation we're using from Singapore represents the magnet as a bunch of tiny magnets or dipoles.
Yeah.
I'm guessing that gives us a more accurate view of what's happening.
Absolutely. It's more realistic than just thinking of the magnet as one big unit.
Right.
Plus, the simulation also shows the current flowing in the ring using these large visualized electrons.
So we can actually see how the strength of that current changes as the magnet falls.
Exactly.
That's pretty cool. Now, I know we have some listeners out there who are probably wondering about some of the finer details of the simulation, like the shape of the signal that it records.
Right.
It has these positive and negative peaks. What do those actually represent?
So those peaks are basically showing us the changing voltage in the ring.
Okay.
Imagine the voltage is kind of like a little push that gets stronger and weaker.
All right.
A positive peak means it's pushing with maximum force in one direction.
Mm-hmm.
And a negative peak means it's pushing with maximum force in the opposite direction.
Okay.
This push and pull is directly related to the changing direction of the induced current.
Interesting. But why aren't the peaks symmetrical?
Yeah.
It's like one side is more dramatic than the other? What's going on there?
Ah, good eye. That asymmetry actually tells us something important about the magnet's movement.
Okay.
Remember how we talked about the magnet falling faster if you drop it from higher up?
Mm-hmm.
Well, as the magnet falls, it's constantly accelerating due to gravity.
Right?
So the magnetic field is changing faster as it goes.
Okay. I'm starting to see the connection here. So the faster the change in the magnetic field, the stronger the voltage.
Yes.
And that's reflected in those taller peaks on the signal.
You got it. Faraday's law in action.
So it's not just about the magnet being inside the ring.
Right.
It's about its entire journey and how its speed affects the magnetic field and the current.
Exactly.
Now, another question that popped up from our listeners, at what point is that magnetic flux changing most quickly?
That would be right when the magnet is in the middle of the ring,
Okay.
where it's moving the fastest.
Makes sense.
It's passing through the most magnetic field lines in the shortest amount of time.
Okay. So we've got Faraday's law telling us about the strength of the induced voltage,
Mm-hmm.
Lenz's law telling us about its direction,
Yep.
and the speed of the magnet influencing everything. Now I see why you said this simple setup demonstrates some pretty fundamental physics principles.
And we're only just scratching the surface. What's even more fascinating is how these principles go way beyond just a magnet and a ring.
Oh,
They explain how we can harness electricity on a massive scale.
hold on. Are you telling me that those giant power plants we rely on for electricity are essentially just a supersized version of our magnet and ring experiment?
In a way, yes. The basic idea is the same.
Wow.
Imagine taking our ring and replacing it with a giant coil of wire.
Mm-hmm.
And instead of a falling magnet, we have a powerful magnet rotating inside that coil.
Okay.
As the magnet spins, it creates a constantly changing magnetic field, inducing a continuous flow of electric current.
Wow. So every time I flip on a light switch, I'm basically harnessing the power of a spinning magnet and a coil of wire.
Pretty much, yeah.
That's amazing. But before we jump ahead to power plants and everyday applications,
Right.
I think we need to dig a little deeper into this simulation.
You're right. We've covered a lot of ground already. Let's take a closer look at how different factors can affect this whole process of electromagnetic induction.
Sounds good to me. And listeners, don't go anywhere. We'll be back in a flash to explore the simulation in more detail.
Welcome back to our deep dive into electromagnetic induction.
So we just left off talking about how the speed of the magnet affects the strength of the voltage.
Right, and something we haven't touched on yet is this idea of magnetic flux. It's a bit of a head scratcher, but bear with me.
Do they love me?
Imagine the magnetic field as like invisible lines of force.
Okay.
Magnetic flux is basically counting how many of those lines are passing through the ring at any given time.
Okay, so the more lines passing through, the higher the flux.
Exactly. Now, as the magnet approaches the ring,
Mm-hmm.
the magnetic flux through the ring increases because remember, the magnet is getting closer and more of those invisible lines are passing through.
Right.
This change in flux is what causes the current to flow in the first place.
So it's not just about the magnet being inside the ring, it's about the entire journey, the approach, the passing through, and then moving away.
Precisely. And each stage of that journey affects the magnetic flux differently.
Okay.
As the magnet moves away from the ring, the flux decreases because fewer lines are passing through.
Right.
But here's the kicker. Lenz's law still applies.
Okay.
The induced current always wants to fight back against that change.
So when the magnet is moving away, the induced current is trying to keep the magnetic flux high. Even though the magnet is getting farther away, it's like it wants to hold on to the magnet's field.
That's a great way to put it. It's like this invisible magnetic tug of war happening between the magnet and the ring throughout the entire process.
Okay, that makes sense. Now, our trusty simulation actually shows us this whole change in flux in action, right?
It does. The simulation can show us how the strength and direction of that induced current are constantly changing as the magnet moves, reflecting those changes in flux.
Mm-hmm.
And remember those peaks on the signal we talked about earlier?
Positive and negative ones that weren't symmetrical?
They're directly related to this change in flux,
Okay.
showing us those variations in the voltage created by the induced current.
Okay. Starting to see the whole picture here. Now, this is where the simulation gets really cool, because we can actually tinker with it and see how different things affect the outcome.
Right. We can play with different variables and see how they impact the whole process.
Yeah.
For instance, let's say we swap out our regular magnet for a super strong one.
Okay.
What do you think would happen to the induced current?
Well, a stronger magnet would mean a stronger magnetic field to begin with, so I'm guessing we'd see a bigger change in flux overall, leading to a stronger induced current.
Exactly. You're on a roll. And you can actually test that out in the simulation and see the effect right on the recorded signal.
Oh, cool.
Those peaks would be even more dramatic.
This is like a physics playground. What other variables can we mess around with?
How about the speed of the magnet? Remember we talked about dropping it from higher up?
Yeah.
What would happen if we made the magnet fall even faster?
Let me think. A faster magnet means the magnetic field changes more rapidly, and if I remember Faraday's law correctly, that would lead to a stronger induced voltage.
You nailed it. And a stronger voltage, of course, means a stronger induced current.
Right.
Bigger peaks galore.
Okay, my mind is officially blown. We can actually see Faraday's and Lenz's laws in action just by tweaking a few things in the simulation. It's not just some abstract idea in a textbook anymore.
That's the beauty of interactive learning tools like this. You can experiment and really get a feel for how these principles work.
Yeah.
Now, one last thing I want to try.
Okay.
What do you think would happen if we used a ring made of a different material? Would that change anything?
Well, we've been using a copper ring this whole time, and copper is known for being a great conductor of electricity, so I'm thinking if we used material that doesn't conduct electricity as well, the induced current wouldn't be as strong.
Right, again, The material of the ring definitely plays a key role.
Okay.
The conductivity of the material determines how easily those electrons can flow through it, which directly impacts the strength of the induced current.
Uh-huh.
You can test different materials in the simulation too and see how it affects the shape of that signal.
So we could try something like rubber, which is an insulator,
Exactly.
and see a much weaker signal.
So we've got the magnet strength, the speed it's falling, and the material of the ring all affecting how this whole induction process plays out. It's incredible to see how these seemingly simple factors can have such a big impact.
Yeah, it really highlights how electromagnetic induction is a dynamic process.
But the good news is, it's governed by those fundamental laws we talked about, Faraday's law and Lenz's law.
Right.
These laws give us a framework to understand and predict how it behaves.
And thanks to the simulation, we can actually see it all unfold before our eyes.
Mhm.
It's making me think about how this principle is at work in so many real-world applications beyond just our magnet and ring setup.
Absolutely. From generating the electricity that powers our homes to the wireless charging technology in our smartphones, electromagnetic induction is truly shaping the world around us.
Okay, I think I'm ready to make that leap from the simulation to real-world applications.
Let's do it.
Listeners, get ready for some electrifying examples in the next part of our deep dive. Welcome back to the deep dive. We've spent the last two parts of this deep dive really getting into the nitty-gritty of electromagnetic induction.
Yeah.
First, with that simple example of a magnet falling through a ring, and then seeing how all sorts of things can affect how that plays out. The strength of the magnet, how fast it falls, even what the ring is made of.
Exactly.
But I think what's really blowing my mind is how this seemingly basic principle is actually behind so many of the technologies we use every single day.
It really is quite remarkable when you think about it. This one fundamental concept underpins a vast array of applications that we often take for granted.
Yeah, like I'm still reeling from the fact that power plants essentially work on the same principle as our magnet and ring experiment.
Let's revisit that for a moment. Remember how we talked about replacing the ring with a giant coil of wire and the falling magnet with a rotating one?
Yep, it's starting to come back to me now.
Well, that's the basic blueprint for an electric generator. Instead of a single drop, you have this continuous spinning motion
Oh, right.
that generates a steady flow of electricity. And by scaling things up, using more powerful magnets, more coils, and spinning them really fast,
Yeah.
we can produce enough power for entire cities.
So every time I turn on a light, I'm harnessing the power of a spinning magnet. That's mind-blowing.
It is, isn't it? And it doesn't stop there. Think about something like wireless charging. How do you think your phone charges without being plugged in?
Honestly, I never really thought about it. It seems kind of like magic.
Well, it's the magic of physics.
Okay.
The charging pad actually creates a changing magnetic field, which then induces a current in a coil inside your phone.
Okay.
And that current is what charges the battery.
So it's like a mini version of the power plant concept, but instead of spinning a magnet, we're using a changing magnetic field to create the current.
Precisely. And the applications go even further. Electromagnetic induction is also the backbone of medical imaging technologies like MRI machines.
Wait, really? How does that work?
MRI machines use powerful magnets and radio waves to create incredibly detailed images of the inside of our bodies.
Wow.
And guess what makes that possible?
Electromagnetic induction. I should have known.
It's everywhere. And this is just what we've discovered so far. As scientists and engineers continue to delve deeper into the intricacies of electromagnetism, who knows what other amazing applications will unlock in the future.
Okay, I think I'm starting to grasp the true significance of what we've been discussing. It's not just a cool science experiment. It's the foundation for so much of modern technology.
Exactly. And it all stems from understanding the fundamental relationship between electricity and magnetism.
So for our listeners out there who might be wondering why they should care about all this, what's the big takeaway here?
The world around us is full of hidden wonders. And oftentimes, the most complex technologies we rely on are rooted in seemingly simple principles. Take this deep dive as inspiration to keep asking questions, keep exploring, and never underestimate the power of scientific curiosity.
Couldn't have said it better myself. We've explored electromagnetic induction from the lab to the real world, and I hope you've gained a new appreciation for this incredible phenomenon. Until next time, keep those minds curious and those magnets spinning.